Current electricity, current electricity 1, current electricity 1, electric current and resistance, electric current and resistance. We shall discuss different topics of this chapter. Number 1 topic is electric current. What is electric current? In the diagram, we have to consider a cylindrical conductor. This is a cylindrical conductor in which free electrons of the conductor will be accelerated towards the positive end of the conductor. This is the free electron which will be accelerated towards the positive end of the conductor, and we can denote the direction of current. Free electrons are accelerated towards left, but electric current I flows towards right. That means here electric current is numerically equal to positive charge divided by time. Positive charge divided by time. That is, electric current is rate of flow of positive charge. Therefore, I is equal to plus Q by T, where plus Q is the charge which is conducted in the opposite direction of free electron. Free electrons are accelerated towards left, but electric current I flows towards right in the opposite direction of flow of free electrons. Therefore, current is a scalar quantity. Current is a scalar quantity which has no definite direction. Current is a scalar quantity. Number 2 topic, we have to define what is drift velocity of free electrons. What is drift velocity of free electrons? Again, we can consider a cylindrical conductor. This is a cylindrical conductor to which a battery of certain EMF is connected, and this is the battery which is connected to the cylindrical conductor XY. The end X has the positive potential and the end Y will be the negative end. Its free electron or the free electron of the conductor will be accelerated towards the positive end of the conductor with a certain velocity Vd. And this certain velocity Vd with which this free electron is accelerated towards the positive end of the cylindrical conductor XY is the drift velocity. And here current I flows towards right, and electric field E is the electric field which acts towards right. M is the mass of free electron. The electrostatic force due to which the free electron is accelerated towards the positive end of the conductor is Fe, and Fe is equal to the product of charge of free electron and electric field intensity. Here Fe is equal to QE into capital E, where Fe is equal QE into capital E, where QE equal minus E, which is the charge of the free electron. Therefore, electrostatic force experienced by the free electron Fe will have what expression? Here it will be minus E dot capital E or only E dot capital E. Here, though the charge of free electron is negative, that means QE equal minus E, but we have to use the magnitude of the charge of the free electron. That's why you have to write Fe as equal small e dot capital E, small e capital E. So Fe is equal small e capital E, which is the electrostatic force experienced by the free electron due to which the free electron is accelerated. Fe is equal to E, which is the electrostatic force experienced by the free electron of the cylindrical conductor xy, due to which it will be accelerated with the drift velocity vd towards its positive terminal. Therefore, electrostatic force vector, that means Fe, vector Fe, in the diagram we can denote the direction of electrostatic force Fe experienced by the free electron. This electrostatic force Fe acts towards left. This electrostatic force Fe acts towards left, which is shown in the figure. Fe acts towards left, and now vector Fe will have what type of expression? It will be minus E vector capital E, or E vector E. Which one is correct? Either whether it is minus E vector E or E vector E. It should be minus E vector E, minus E vector E, because electric field intensity acts towards right, and this electrostatic force experienced by the free electron acts towards left. That's why the electrostatic force Fe and electric field intensity vector E are opposite to each other, and hence vector Fe equal minus E vector E. Again, Fe is equal mass into acceleration of the free electron. Electrostatic force is equal mass into acceleration. Therefore, Fe is equal m Vd by tau. Vd is the drift velocity, tau is the relaxation time, where tau is the relaxation time. That is the interval of time between two successive collisions of free electron with the positive ion of the conductor. Tau is the relaxation time, which is the interval of time between two successive collisions of the free electron with the positive ion of the conductor. Now we can denote equation 1 and 2. Fe is equal to EE, that was equation 1. Now Fe is equal m Vd by tau, that is equation 2. If we compare equation 1 and 2, then we get Vd will be equal EE by m bracket close into tau, which is the drift velocity of the free electron. Vd equal small e capital E divided by m bracket close into tau, which is the drift velocity of the free electron. And what about the vector expression of drift velocity? Vector Vd equal minus E vector E by m into tau. Vd is of the order of 10 to the power minus 5 meter per second. And orbital velocity of electron revolving around the nucleus is of the order of 10 to the power 6 meter per second, where V0 is the orbital velocity. V0 is the orbital velocity of bound electron revolving around the nucleus, of an atom. Vd drift velocity is of the order of 10 to the power minus 5 meter per second, but orbital velocity V naught is of the order of 10 to the power 6 meter per second. Now we have to discuss what is relaxation time. What is relaxation time? We can draw a cylindrical conductor in which free electrons are accelerated towards its positive terminal of the conductor. This is the free electron which is accelerated along this direction with certain drift velocity Vd, and it will collide with the positive ion. This is the free electron which is accelerated towards a certain direction, and this free electron reaches to this point at instant t equal t1 second, and it collides with the positive ion of the conductor, and this free electron will be deviated along this direction due to the collision with the positive ion, and this free electron will again collide with another positive ion of the conductor at instant t equal t2 second. After the collision, this free electron will be deviated along that direction, and the free electron collides with the second positive ion at the instant t equal t2 second, and Vd is the drift velocity with which free electrons is accelerated towards the positive terminal of the conductor. Now Relaxation time is tau, which is equal. Relaxation time is tau, which is equal. What we know, it will be T1, T2 minus T1 or T1 minus T2. Which one is correct? Relaxation time. So at t equal t1, it collides, it undergoes first collisions, and t2 is the time at which it collides with a positive ion, or it undergoes second collision. That's why tau will be equal to t2 minus t1. That is the relaxation time. Relaxation time is is tau, which is equal t2 minus t1, which is the relaxation time. Time tau is of the order of 10 to the power minus 14 second. Tau is the order of 10 to the power minus 14 second. Now next topic is what? Next topic will be expression of current flowing through a conductor. Expression of current flowing through a conductor. This is the diagram, and free electron of the cylindrical conductor xy will be accelerated with the drift velocity vd towards the positive terminal of the conductor, and current I is the current which flows towards right, and E is the electric field intensity which acts from positive to negative terminal of the conductor. M is the mass of free electron, and we can assume that the free electron starts to move from the negative terminal at instant t equals 0 second. And here current I is equal to q by t, that is the rate of flow of positive charge. I is equal to q by t, where q is equal n dot q e. N is the total number of free electrons, and QE is equal to E, which is the charge of free electron. Now, number of free electrons is capital N, which is equal to small n under bracket A dot small l, where small n is the number of free electrons per unit volume of the conductor. That means small n is the free electron density, and capital N is the total number of free electrons in the conductor xy. Therefore, total charge of the conductor, that is small q, is equal small n A L E. Q is the total charge of the conductor xy, or total charge that flows through the conductor in time t. In time t, though free electrons have negative charge, but we have to consider the rate of flow of positive charge through the conductor xy in time t, and that is equivalent to electric current. I is equal to q by t, which is equation 1, and q, that is the amount of charge which flow through the conductor, is small q. Now the time taken by a free electron to travel a distance L, which is equal to the length of the conductor xy, is t, and that will be equal to L by Vd. L is the length of the conductor and Vd is the drift velocity. Here we can assume that the free electron travels a distance L, which is equal to the length of the conductor xy from the end y to x, that is from the negative end to positive end of the conductor, and the distance traveled by this free electron to travel along the length of the conductor is L, which is equal to Vd dot t. Vd is the drift velocity, t is the time taken by the free electron to travel the distance L, which is equivalent to length of the conductor with the drift velocity Vd in time t. In time t, the free electron travels from the end y to x in time t with the drift velocity Vd. Therefore, T is equal L by Vd, which is the time taken by a free electron to travel from negative end to positive end of the conductor, and in this case T is equal to L by Vd. Therefore, I is equal to Vd dot small e dot small n dot capital A, which is the current expression of current flowing through a conductor in terms of drift velocity Vd and free electron density small n. I is equal to Vena Vd dot E dot N dot A, where Vd is the drift velocity of free electron and n small n is the number of free electrons per unit volume, small n equal to capital N by A dot L, which is the free electron density, free electron density is small n. Capital N is the total number of free electrons of the conductor xy. Small n is the free electron density, and free electron density small n is of the order of 10 to the power 28 per meter cube. N is of the order of 10 to the power 28 per meter cube. And dimension of free electron density, that means the dimension of n. Now free electron density, that means small n has the unit meter to the power minus 3 or meter cube inverse. That's why dimension of n is L to the power capital L to the power minus 3. Now we can denote the direction of electric current I. Electric current I flows through the conductor xy towards right, that means from positive n to negative n. That is, current flows from the end x to y. Now we have to state Ohm's law. What is Ohm's law? For that we can draw a conductor or resistor of resistance R. A and B are the two terminals of this resistor R. V is the potential difference across this resistor of resistance R. VA and VB are the potentials at the two terminals A and B of the resistor. We can assume VA greater than VB. That's why electric current I flows towards right, that means from the end A to B through the resistor R. And what should be the mathematical expression of Ohm's law? We know that potential difference across the resistor is V, which is equal to VA minus VB. Now Ohm's law is what? I proportional V. That means current flowing through the resistor or conductor is directly proportional to the potential difference across the resistor or conductor AB, provided temperature, other physical conditions remain unchanged. So Ohm's law, according to Ohm's law, current flowing through a resistor or conductor is directly proportional to the potential difference, that is I proportional V. Now we have to know which physical conditions remain unchanged. In this case, physical conditions are such as temperature, pressure, or presence of magnetic field, intensity of light, mechanical strain, etc. Are kept constant. Physical conditions such as temperature, presence of magnetic field, intensity of light, mechanical strain or stress, etc. are kept constant. Now we can explain or discuss proof of Ohm's law. We have to draw the same diagram. That means a conductor XY of length L are connected to a battery of terminal voltage V. V is also the potential difference across the conductor XY, and we know the expression of current I. Here current I can be written as any VDA also. It can be expressed as Vena, and also it can be written as any VDA. Electric current flowing through the conductor XY is I, which is Vena Vd dot E dot N dot A, where Vd is the drift velocity with which free electrons will be accelerated, and Vd has the expression E by small m into tau. Capital E is the electric field which is acting across the conductor XY. Therefore, expression of current I is equal to E by M into tau E N A. I is equal to N square tau by M into A into into capital E, where capital A is the area of cross section and capital E is the electric field intensity which is acting from its positive end to negative end of the conductor. Electric field intensity E is numerically equal to V by L, potential difference divided by length of the conductor. Now, electric field intensity is negatively equal to potential gradient. That is, E is equal electric field intensity E equal minus dV by dr, where dV is the potential difference between the two ends x and y of the conductor and dr is the distance between the two ends. Therefore, E is equal minus in place of dV, in place of potential difference dV between the two ends x and y, what we can write 0 minus V divided by L in place of dV. Now potential at the end y is 0. Potential at the end x of the conductor is V. That's why in place of dV we can write 0 minus V, and in place of distance dr we can write down the length of the conductor ly. That's why we get field intensity E as V by L. Therefore, the expression of current I will be N square tau divided by M A by L dot V. Therefore, we get the expression of current N square tau. We get the expression of current I as N square tau by M A by L dot V. A by L dot V. We get the expression of current I in terms of V, and therefore you can say that I proportional V as N E tau M A L, all are constant. That's why I will be proportional to V. That means electric current flowing through the conductor will be directly proportional to the potential difference V. I proportional V, this is Ohm's law. Expression of resistance of a conductor. Now the current flowing through a conductor is I, which is equal to VDENA. Now putting the expression of drift velocity VD in the expression of I, we get I as equal N squared tau by M A by L dot V. Therefore V equal to M divided by N squared tau L by A into I. That is the expression of V. That means V is the potential difference across a conductor or resistor. Again, potential difference V is equal to R into I, where R is the resistance, which is equation 2. We get the two expressions of potential difference V. Therefore, the resistance R will be equal M divided by N squared tau into L by A. This is the expression of resistance R equal M divided by N squared tau into L by A. That is the electric resistance of a conductor. Electric resistance of a conductor. Also resistance R is equal to rho L by A, where rho is the resistivity or specific resistance of the conductor. If we compare these two expressions, we get rho as M divided by N squared tau. Rho equal M divided by N squared tau. This is the expression of resistivity or specific resistance of the conductor. Resistivity or specific resistance of the conductor. Therefore, we can say that resistance R is directly proportional to L length and R is inversely proportional to area of cross section A. Now we shall discuss what is microscopic form of Ohm's law. Now we can discuss microscopic form of Ohm's law. This is a conductor, a current I flows towards right through the conductor. We can denote area of cross section of the conductor. A is the area of cross section. R is the resistance of the conductor. Rho and sigma are what resistivity and conductivity. where sigma is equal to 1 by rho, which is the conductivity of the conductor. Rho is the resistivity. That's why conductivity is reciprocal of resistivity. Now we know that the current density of the conductor is the electric current divided by area of cross section. Therefore, J is equal to I by A, equal, putting the expression of current, which is Vena divided by A, and we get J as equal Vd dot E dot small n, where small n is free electron density, equal E by m into tau E n. Finally, we get n squared tau by m into capital E. J is equal to n squared tau by m into E. Therefore, J is equal to 1 by rho into E, where rho is equal to m divided by n squared tau, which is the resistivity. Finally, we get J as equal sigma E. J equal sigma E, which is the microscopic form of Ohm's law. That is, current density is numerically equal to the product of conductivity sigma and electric field intensity E. Now, what will be the vector expression of microscopic form of Ohm's law? Vector J will be what? Sigma dot vector E, or vector sigma E, or sigma vector E. Vector J will be equal to sigma vector E. Sigma vector E. Correct form of microscopic form of Ohm's law in vector expression is vector J equals sigma vector E. That means current density vector is equal to conductivity sigma into electric field intensity vector E. Now, conductance G is equal to 1 by R. G is equal 1 by R, that is the conductance, and conductivity sigma is equal to 1 by rho, that is conductivity. G is conductance, sigma is conductivity, and conductance is equal 1 by R, that is reciprocal of resistance. Unit of rho is ohm meter. Unit of resistivity rho is ohm meter, because rho equal to resistance R into area divided by length. Now, unit of sigma will be mho meter inverse. Unit of conductance G is ohm inverse or mho. Ohm inverse or mho or Simon. Ohm inverse or mho or Simon. That is the unit of conductance. Now we shall discuss what will be the effect of temperature. Effect of temperature on the resistivity or resistance of a conductor. We know the expression of resistivity rho equal m divided by n squared tau. Therefore, rho proportional 1 by tau means resistivity is inversely proportional to relaxation time. If the temperature theta is increased, if the temperature of the conductor or metallic conductor is increased, frequency of collision of free electrons with the positive ions of the conductor. If the temperature theta is increased, frequency of collision of free electrons with the ions of the conductor also increases. This frequency of collision of free electrons with the ions is denoted by nu. If the temperature is increased, frequency of collision also increases. Hence, it reduces relaxation time tau. It reduces the relaxation time tau, where relaxation time is the time interval between two consecutive collisions of free electrons with the positive ions of the conductor. Therefore, resistance or resistivity rho under bracket m divided by n squared tau. N squared tau increases as relaxation time tau decreases. Hence, resistance of the conductor or metal also increases. In this case, what happens if the temperature is increased, frequency of collision of free electrons of the conductor with the positive ions increases, it reduces or it decreases the relaxation time tau, and we know that resistance or resistivity is inversely proportional to relaxation time. That's why if temperature is increased, relaxation time decreases and resistivity of the conductor increases. In this case, what will be the topic? Effect of temperature on resistance of a conductor or metallic conductor. Effect of temperature on a resistance on the resistance of a metallic conductor or conductor. Now, next in the next topic, we shall consider resistance of a metallic conductor or conductor as R0 at 0 degree C, and resistance changes to RT at temperature theta T equal 0 degree C. In this case, temperature of the conductor is increased from theta 1 to theta T degree C, theta 1 to theta T degree C. Here we can change or we can express the temperature as, final temperature as T degree C and initial temperature as 0 degree C. Now, resistance of the conductor at T degree C, RT, can be written as R0 1 plus alpha delta T, where delta T is T minus 0 degree C, which is equal T degree C, which is the change in temperature. Therefore, RT is equal R0 bracket open 1 plus alpha T. RT equal R0 1 plus alpha T. RT equal R0 1 plus alpha T, which is the resistance of the conductor at T degree C or at the final temperature T degree C, where alpha is equal to RT minus R0 divided by R0 into delta T, which is the temperature coefficient. Alpha is the temperature coefficient of the electric resistance, temperature coefficient of the electric resistance. Unit of alpha is Kelvin inverse or degree C inverse. RT is the resistance of the conductor at T degree C, R0 is the resistance of the conductor at 0 degree C, and alpha is the temperature coefficient of the electric resistance. Now for metal, change in resistance due to rise in temperature, that is RT minus R0, will be positive. That means RT minus R0 greater than 0. Therefore, alpha greater than 0, as alpha equal RT minus R0 divided by R0 into delta T. That means for metal, temperature coefficient of resistance is positive as resistance increases due to rise in temperature. Now for semiconductor, as an example, silicon or germanium, RT minus R0 for semiconductor or insulator, change in resistance, that is RT minus R0 less than 0 means negative. Therefore, alpha is also negative. So here for metal, alpha greater than 0. For semiconductor, alpha means temperature coefficient of resistance is negative. And for certain alloys such as constantan, manganese, eureka, RT minus R0 is equal to 0. That means change in resistance is 0. That's why alpha equals 0. That means for certain alloys such as constantan, manganese, eureka, the temperature coefficient of resistance is 0. That means if temperature is changed, resistance remains unchanged for that certain alloys like constantan, manganese, eureka. Next topic is what resistance versus temperature graph. Number 1, for metallic conductor, for metal or metallic conductor, we know that if temperature is increased, resistivity increases linearly in a certain range of Temperature. Resistivity rho is plotted along vertical axis. Absolute temperature capital T, or temperature in Celsius scale, is plotted along horizontal axis. T, small t, is the temperature in Celsius scale. We can draw an imaginary straight line. This is an imaginary straight line in rho versus T graph. Rho is the resistivity, small t is the temperature in Celsius scale. So we can assume an imaginary straight line. This is an imaginary straight line along which resistivity increases linearly with temperature within a certain range of temperature. This is the straight line along which resistivity of metal increases linearly, and at the lower portion resistivity increases following a curve, and at the higher temperature or at high temperature resistivity increases following a curve. Between A to B, resistivity of metal increases linearly with the temperature in Celsius scale. But in this range, or in that range, in lower temperature or in higher temperature, resistivity increases following a curve. But in the range AB, resistivity changes. In the range AB, resistivity changes, that is, increases linearly with temperature in Celsius scale. And if we draw an imaginary line, uh, at this point temperature will be 0 degree C or 273 Kelvin, and resistivity at 0 degree C will be rho 0. Number 2, we have to plot rho versus temperature graph for semiconductor. We have to plot resistivity versus temperature graph for semiconductor. Rho is the resistivity, T is the temperature. Rho is the resistivity and T is the temperature. Resistivity of semiconductor decreases with the temperature exponentially. Resistivity of semiconductor decreases exponentially with the rise in temperature. Here the resistivity decreases as according to this exponential graph with the temperature. That means if temperature is increased, resistivity of the semiconductor decreases exponentially. And at the low temperature, there should be distance between the resistivity axis and the graph. And at the high temperature range, there should be distance between the graph and the temperature axis. And obviously, resistivity decreases with rising temperature exponentially. Here, what we can see, that is, as according to the graph, resistivity of semiconductor decreases exponentially with the temperature, with the absolute temperature of the semiconductor. Along x-axis, absolute temperature capital T should be plotted. And number 2, if we plot resistivity versus absolute temperature for certain types of alloys such as manganese, constantan, and eureka, then we get this type of graph. Rho versus T graph. Rho 0 is the temperature at absolute 0 Kelvin temperature, and this resistivity graph will be parallel to the temperature axis. What is the effect of temperature on the resistance of a semiconductor? What is the effect of temperature on the resistance of a semiconductor? We can draw conduction band and valence band of a semiconductor. The higher energy band is known as conduction band, and the lower energy band is known as the valence band, or VB. there will be a number of valence electrons in the valence band. These are the valence electrons which exist in the valence band. Few valence electrons will jump from valence band to conduction band. Few electrons will travel from valence band to conduction band. These are valence electrons in valence band of the semiconductor, and the these electrons which jump to conduction band are known as conduction electrons. Electrons in conduction band are known as conduction electrons, and the empty space of positive charge in valence band are known as holes. This empty space of positive charge from which valence electrons travel from valence band to conduction band are known as hole, and the energy gap between conduction band and valence band is the forbidden energy gap Eg. V dot V means valence band, which has low energy, and this is a number of straight lines or energy levels, and which is valence band, and a branch of energy levels is also known as conduction band. Cb means conduction band. Eg is a forbidden energy gap. Eg is a forbidden energy gap. Eg is the forbidden energy gap between conduction band and valence band. No electrons exist in this gap. That's why it is called as forbidden energy gap. Energy band diagram, and this is the energy band diagram in which we have conduction band and valence band, and number of electrons per unit volume has the expression n equal n0 e to the power minus eg by 2 kt, where k is the Boltzmann constant and T is the absolute temperature of the semiconductor. So n is the number of conduction electrons per unit volume in the conduction band. This is the number density of conduction electrons, not only the number of conduction electrons. It should be number density of conduction electron. K is the Boltzmann constant, which has the value 1.38 into 10 to the power minus 23 joule per Kelvin. Kb is equal to 1.38 into 10 to the power minus 23 joule per Kelvin. In this case, n is the number of conduction electrons in conduction band per unit volume. If the temperature or absolute temperature capital T is increased, Eg by 2 kt decreases, and minus Eg by 2 kt increases. Minus Eg divided by 2 kt increases. Hence, we can say that the number of conduction electrons. So n is the number density of conduction electrons. If the temperature T is increased, then the number density of conduction electrons in conduction band, that is small n, equal E0 n0 e to the power minus Eg by 2 kt also increases. Hence conductivity under bracket sigma increases. Conductivity of semiconductor increases, and resistivity rho equal 1 by sigma of the semiconductor decreases with the rise in its absolute temperature. Resistivity of semiconductor decreases exponentially with its absolute temperature. If the temperature T is increased, in that case number density of conduction electrons in conduction band increases. That's why conductivity increases, resistivity of semiconductor decreases exponentially. We can draw conductivity versus absolute temperature graph. Conductivity increases exponentially with its absolute temperature. If we plot resistivity rho with its absolute temperature, In that case, resistivity of semiconductor decreases exponentially as shown in the figure. And at low temperature there should be distance or separation between resistivity axis and the graph. Now we have to know what is non-ohmic conductor. What is non-ohmic conductor? Non-ohmic conductor does not obey Ohm's law. Does not obey Ohm's law. That means for non-ohmic conductor, uh, I is not proportional to V. What is Ohm's law? Current I is directly proportional to potential difference. If we plot I versus V graph, then we get if V is increased, current I increases following this type of curve, which is applicable for non-ohmic conductor. Example of non-ohmic conductor is semiconductor. Number two, semiconductor diode is non-ohmic conductor. Liquid electrolysis, liquid electrolyte is also another example of non-ohmic conductor. Transistor, uh, diode, triode are few examples of non-ohmic conductor. Non-ohmic conductor does not follow or obey Ohm's law. According to Ohm's law, I proportional V, but for non-ohmic conductor, current I is not directly proportional to the potential difference V. Next topic, what is superconductivity? What is superconductivity? That is, we have to know. For superconductor, resistivity rho is 0 and conductivity sigma is infinity. That means superconductor has infinite conductivity. Mercury becomes superconductor. Mercury becomes superconductor at 4.2 Kelvin absolute temperature. What are the uses of superconductor? Uses of superconductor are what? Number one, it is used to produce very high speed computer. It is used to produce very high speed computer. Number two use, superconductor. Superconductor are also used for the transmission of are also used for the transmission of electric power. Now determination of resistance determination of resistance of carbon resistor using color code. We can draw a carbon resistor. This is a carbon resistor. There are four different color strips. These are the first three color strips with color red, yellow, and violet, and there will be fourth color strip. In this case, and the fourth color strip is D. D is the fourth color strip. Now, value of resistance of carbon resistor is capital R equal AB into 10 to the power C ohm plus minus D percent plus minus D percent, and D indicates the tolerance of or accuracy. So the value of resistance of carbon resistor is given by capital R equal AB into 10 to the power C ohm plus minus D percent. First two color bands indicate the first two significant figures. Of the value of resistance. First two color bands indicates the first two significant figures of the value of resistance, and the third color strip, that is the color strip C. Third strip, The third colored strip, that means the strip C, indicates the decimal multiplier, of the resistance. The value of A, comma B and C will be derived or will be determined by the value of first three color strips. That means the value of ABC will be determined as according to the following code. For that we have to memorize this code. BB Roy, Great Britain. Very good wife. BB Roy, Great Britain, very good wife. Now this underlined letter stand for what? This G is green, this B is black, and that B is brown, and this G is green, and this B stands for blue, and this G stands for gray. W stands for white. W stands for white. So this letters, 10 letters indicate the different values of first two significant figures of resistance. That is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. This underlined letters indicate the different colors having different values. Now significance of fourth color strip. Significant of fourth color strip is what tolerance will be 5% if the fourth color strip D is gold, 10% if the fourth color strip D is silver, and 20% if there is no fourth color strip. That means D is has no color. Significant. This is the significance of fourth color strip. Now we can write down the code again. B. Roy, Great Britain, very good wife. Great Britain, very good wife. Now we can underline the letters, and these letters have different values. That is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And the value of resistance is R equal AB into 10 to the power C ohm plus minus D%. Now in this carbon resistor, first color strip is red color, which has the value 2, and second color strip is yellow, and which has the value 4. Third color strip, which indicates the decimal multiplier, is violet, having value 7, and the fourth color strip is silver, which indicates the value of tolerance, which is equal to 10%. Therefore A equal to 2, and B is equal to 4, and C is equal to 7, and D equal to 10%. Therefore the value of resistance of carbon resistor will be R equal 24 into 10 to the power 7 ohm plus minus 10%. R equal 24 into 10 to the power 7 ohm plus minus 10%. This is the value of resistance of the carbon resistor, which is derived by using the color code of this carbon resistor. For this carbon resistor, we can write down the code again. BB Roy, Great Britain, very good wife. Great Britain, very good wife. Writing the first letter of that code, and different values of these letters are given, and the value of resistance will be R, which is 85 into 10 to the power 2 ohm plus minus 20%. The first color strip is silver, that's why the first significant of resistance is 8. Second color strip is green, that's why the second significant figure is 5. Third color strip is red, that's why the power of 10 is 2. And the value of resistance is 8500 ohm, and 20% error over 8500 ohm will be 1700 ohm. In this way you can find the tolerance or accuracy. Percentage error in the measurement of resistance is delta R by R into 100 will be 1700 or 1700 ohm. That is the tolerance in the measurement of resistance. Now we can consider another case. The value of resistance of a carbon resistor will be given. The value of resistance of a carbon resistor is given as 76000000 ohm plus minus 5%. Find the color code. Find the color strips of the carbon resistor. Color strips of the carbon resistor. Now we can write down the value of resistance R equals 76000000 ohm. That can be written in terms of two significant figures with the decimal multiplier. That will be 76 into 10 to the power 6 ohm. 76 into 10 to the power 6 ohm. And 7 stands for violet, 6 stands for blue, and the power of 10 is also blue. So first color strip is violet, second color strip is blue, and the third color strip will be again blue. And the fourth color strip will be what? The fourth color strip will be what? It will be gold, because fourth color strip is gold, and tolerance or accuracy is 5%. That's why fourth color strip is gold. Next topic is we have to discuss the series combination of resistances. R1, R2, R3 are the three resistances which are connected in series combination. I is the current which are flowing through the three resistances. V1, V2, V3 are the potential differences across the three resistors. Now the equivalent resistance Rs will be equal to R1 plus R2 plus R3. Rs is equal R1 plus R2 plus R3, which is the equivalent resistance of the series combination. If R1 is the greatest resistance of the series combination, R1 is the greatest resistance, and R2 plus R3 is equal X. Now for a series combination of n number of resistors, equivalent resistance Rs is equal to R1 plus R2 plus R3 dot 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 dot. If R1 is the greatest resistance and R2 plus R3 plus dot 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 is equal to X, then Rs is equal to R1 plus X. Rs can be written as R1 plus X. Therefore, Rs greater than R1, as Rs is equal to R1 plus X. Now, equivalent resistance, that is Rs, is greater than the greatest resistance R1. Rs is greater than R1. That means equivalent resistance in the series combination is greater than the greatest resistance. Now we can discuss parallel combination of resistances or parallel combination of resistors. This is a parallel combination, and R1, R2, R3 are the resistances which are connected in parallel combination. I is the main current, which is split into three currents, I1, I2, I3, that will be flowing through R1, R2, R3. V is the potential difference across all the resistances. Potential difference V will be same, but currents will be different. In that case, 1 by Rp is equal to 1 by R1 plus 1 by R2 plus 1 by R3. Therefore, Rp equal R1, R2, R3 divided by Rp equal R1, R2, R3 divided by R1, R3 plus R1, R2 plus R2, R3. R1, R3 plus R1, R2 plus R2, R3. That is the equivalent resistance of the parallel combination. For n number of resistances in parallel combination, 1 by Rp equal 1 by R1 plus 1 by R2 plus 1 by R3 plus dot 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 1 by Rn. Let R1 is the least resistance. R1 be the least resistance, and 1 by R2 plus 1 by R3 plus dot 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 plus 1 by Rn is equal to X. Therefore, 1 by Rp equal 1 by R1 plus X. Therefore, 1 by Rp greater than 1 by R1. Therefore, Rp less than R1. Rp less than R1. Hence we can say that the equivalent resistance of the parallel combination of resistors is less than the least resistance. The equivalent resistance is less than the least resistance in the parallel combination for the parallel combination of resistors. What is internal resistance of a cell or battery? Internal resistance of a cell. We can draw a cell. This is an electric cell having positive and negative plate, and this is the electrolyte between the two plates. The medium between the two plates or electrodes is electrolyte, and this is positive electrode or positive plate, and this is the cell, and the cell has negative electrode also. Internal resistance, that is internal resistance is the resistance offered by the electrolyte and electrodes. It is the resistance offered by the electrodes and electrolyte of the electric cell. It is the resistance offered by the electrodes and electrolyte of the cell, and it depends upon, we can denote EMF E, and R is the internal resistance in the diagram. It depends upon the distance between the two electrodes. It depends upon the distance between the two electrodes of the cell. Number 2, nature of electrolyte. Number 3, area of cross section of each electrode or plate. Area of electrodes. So now, in what way internal resistance depends upon the distance between the two electrodes? This are the two electrodes. D is the distance between the two electrodes. R, small r, is the internal resistance, which is denoted in the diagram. Now we have to mention in what way internal resistance depends upon the distance. Here the internal resistance increases. Internal resistance increases. Internal resistance increases with the distance, with the increase in distance between the two plates, increase in distance between the two electrodes or two plates. And also we have to mention in what way internal resistance depends upon the area of electrodes. Internal resistance of the electric cell decreases with the increase in area of the plate or of the electrodes. Internal resistance of a cell decreases with the increase in area of the electrodes. That means internal resistance is inversely proportional to area of cross section. Terminal voltage of an electric cell or battery. Terminal voltage of a battery. We can draw a diagram of a battery or electric battery, and an external resistance capital R is connected to this battery. Small r is the internal resistance of the battery. Capital R is the external resistance which is connected in parallel with the battery of EMF capital E. I is the current which is generated from positive electrode of the battery, and it flows from positive electrode to negative electrode outside the battery, and this current I flows from negative electrode to positive electrode inside the battery. The current flows from negative to positive electrode of the battery inside the battery or through the internal resistance of the battery, but this current I flows from positive electrode to negative electrode outside the battery. V is the terminal voltage of the battery of EMF E, and also same voltage or potential difference is V, which is obtained across the resistance R. And this two terminal voltage of the battery and potential difference across the external resistance R will be same. Now V equal potential difference across the battery. V is equal potential. V is the terminal voltage, which is the potential difference across the battery in a closed circuit. This is the definition of terminal voltage. V is the terminal voltage, which is equal to the potential difference across the battery in a closed circuit. E is the EMF, which is the potential difference across the battery or cell in an open circuit. In an open circuit, E is the EMF of the battery, which is the potential difference across the battery in the open circuit. E is the EMF of the cell or the battery, and V is the terminal voltage of the battery in closed circuit, and E is EMF, which is the terminal voltage of the battery or cell in open circuit. Now we can write down the relation between terminal voltage and EMF. V equal E minus I dot R. V equal E minus I dot R during discharging of the cell, because current is drawn from the battery to the external resistance. That's why during discharging of the battery or cell, terminal voltage V will be equal to EMF minus I dot R, E minus I dot R. That means in words what you can write, V is terminal voltage is equal to EMF minus lost volt. V is the terminal voltage, E is the EMF, and I dot small r is the lost volt. Terminal voltage is equal EMF minus lost volt. EMF minus lost volt. That's why here the lost volt is I dot small r, where small r is the internal resistance of the battery. Lost volt is the product of current I and internal resistance small r. Also, we can prove the same relation, that is terminal voltage equal to EM minus lost volt, using Kirchhoff's voltage law. Using Kirchhoff's voltage law in the closed loop, ADCBA, we get summation of all the voltages will be 0, summation V 0. And if we start from the point A and move along ADCBA, then we get the first potential difference across the external resistance capital R. If we start from A and travel along ADC, we get the first potential difference across the external resistance capital R, and that means plus VDC plus I dot small r minus E equal 0. VDC plus IR minus E equals 0. Across the external resistance capital R, the potential difference is VDC. And across the internal resistance small r, potential difference is I dot small r. And current I flows in the same direction along BA. That's why I dot R is positive. And current I is flowing towards left, and we are also traveling from B to A. That's why potential difference across the internal resistance small r is positive. That means I dot R is plus I dot R. Now if we want to cross the EMF or the battery, we have to cross the first negative electrode of the battery. That's why EMF. Here we have to cross the first negative electrode, then positive electrode of the battery. That's why EMF will be negative. Here in the equation we have minus E. Because to travel from B to A or to cross the battery of EMF E, we have to cross first negative electrode, then positive electrode of the battery. That means we have to travel in the opposite direction of increasing voltage. That's why EMF E will be negative. So VDC plus I dot R minus E equal 0. Similarly, if we consider the closed loop ABCDA, if we travel along ABCDA, then Kirchhoff's voltage law will be plus E minus I dot R minus VDC will be equal 0. So in the main expression, we can write VDC equal E minus I dot R. Therefore, V equal E minus I dot small r. That means terminal voltage V will be equal to EMF E minus lost volt. That means I dot small r. And this is the relation between terminal voltage V and EMF E during discharging of the battery. During discharging of the battery. And if we consider the charging of the battery, and now across the external resistance capital R, VDC is equal to V, which is equal to I dot capital R. That is also the potential difference across the external battery. I dot R will be equal to E minus I dot R, I dot small r. I dot capital R. Now finally we get small r equal E by V minus 1 into capital R. Small r is equal E by V minus 1 into capital R, which is the internal resistance, or which is the expression of internal resistance of the battery in terms of external resistance capital R. If we consider charging of a battery, in that case the battery of EMFE internal resistance R is connected to a source. The source sends the current I towards the positive electrode of the battery. V is the terminal voltage of the battery. In this case, V will be equal to E minus under bracket minus R into R, because current I flows in the opposite direction. We get V as equal E plus I dot R. V as equal E plus I dot R, which is the terminal voltage of the battery during charging. V equal E plus I dot R during charging of the battery. That means terminal voltage. So here terminal voltage V will be greater than the EMF of the battery. EMF of the battery during charging of the battery. But during discharging, V is less than E. That means terminal voltage will be less than the EMF. V less than E during discharging, but V greater than E during charging of the battery. V less than E during discharging of the battery.